Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. Every week on Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries that are revolutionizing our world and touching our lives. Well, perhaps you've heard the news. We may actually have a traffic jam over Mars. That's right. 3 groups, count them, 1, 2, 3, 3 groups have announced that they want to send a mission to Mars. And these are just not science fiction writers or visionaries or whatever. No. The first is Elon Musk of SpaceX, the founder of PayPal, a billionaire, also Tesla Motors, and he wants to send an unmanned rocket to Mars by 2024 and then a manned mission soon after that. And get this, he wants to create the first city on Mars. He envisions 1,000, count them, 1,000 rockets being sent to Mars, each one with 100 colonists. Of course, that'll take decades to get off the ground, but his first milestone is 2024. And then, not to be outdone, Boeing Aircraft has said, not so fast. We want to send a mission to Mars because we're going to build a rocket. We're going to build a rocket that takes us to Mars. And then, not to be outdone anymore, President Barack Obama has now given the seal of approval. NASA's next mission will be to Mars. You know, for years, NASA was called the agency to nowhere. It just spun wheels. The space shuttle, for example, can't even go to deep space. It simply spins wheels around the planet Earth. And ever since the moon program was closed down, humans have never ventured outside the gravity well of the planet Earth. And the President of the United States has now stated that the goal of NASA is, in fact, Mars perhaps within 20 years, meaning that sometime in the 2030s, we don't know for sure, we're going to go to Mars. First, we have the booster rocket, the SLS booster rocket, now being tested. This is not simply paper pushing on the part of a bureaucrat. We're talking about hardware. Hardware being tested. The SLS is even bigger than the Saturn rocket, which took us to the moon. And then we have the Orion module. The Orion module was to be the replacement for the space shuttle, but the space shuttle was canceled by the president. But they salvaged the space module of the Orion to be on the mission to Mars. And in fact, he even laid out a 3-point program. The first phase of the mission will be to test the SLS booster rocket and the Orion space module. That's step 1. Step 2 is to actually fly the whole rocket to the moon as a test. In other words, we're going to go to moon just as a test to go to Mars. And then in part 3 of the mission, we may go to an asteroid, or we may go to a moon of Mars, or we may actually go all the way to the red planet. And so with us today to discuss all of this is Chris Hadfield, a Canadian astronaut. He's been on 3 space missions, 2 on the space shuttle to the International Space Station and 1 on the Soyuz spacecraft, which he commandeered actually was the commander of the Russian Soyuz mission to the space station. After the break, we're going to bring on Chris Hadfield, Canadian's first astronaut. He piloted 3 space missions, including the Soyuz spacecraft, and we're going to talk about the exploration of Mars.
You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. We're going to blast into outer space with Chris Hadfield, the first Canadian into outer space. He was actually on 3 space missions, and everyone is talking about Mars. President Barack Obama has recently stated that, yes, Mars is the goal. In fact, in 20 or so years, we don't know for sure, we expect to have the first manned mission to the red planet. So with us today to talk about all the joys and tribulations and dangers of space travel is Chris Hadfield. Once again, he was the first Canadian to go into outer space. He spent 35 years with the military in the space program. He's been on 3 space missions, 2 on the American space shuttle and 1 commanding the Soyuz space capsule. So, Chris, glad you could be on Science Fantastic.
My pleasure, Michio. Nice to be talking with you.
Okay, first question is, how did you as a youth first get interested in science?
Well, I started with science fiction, I think, like a lot of people. I read Arthur C. Clarke and Edgar Rice Burroughs and all of the fantastic mind-stretching ideas of fiction, and then not just the books, but images with movies like 2001: A Space Odyssey, and then, of course, Star Trek on television. All of those things kind of, I think, laid the foundation of what might be possible. Sort of like when you're talking about Mars, Michio. It's still right on the edge of impossible, but it sure does expand your mind. But it was the reality of space flight that really got me interested when the very first human beings were flying in space, and then the seminal moment when the first 2 people walked on the moon. I was a kid just about to turn 10, and watching Neil and Buzz put their footprints in the dusty gray surface of the moon. That's really what got me hugely interested in space flight and all of the science that goes along with it.
Okay, well, you joined the Canadian Armed Forces, but what was the moment? What was the moment that you said to yourself, I just don't want to fly planes in the atmosphere. I want to go rocketing into outer space. Was there a moment that finally tipped you over to become an astronaut?
Yeah, it was July 20th, 1969. I know the exact moment. It was sitting in a living room with, a living room packed with people, all watching that first moon landing. And it was really that idea. You know, I'm from Canada. We didn't have astronauts at the time. We didn't have a space agency. But to see something impossible happen, to see something that had never happened before suddenly turn into a reality, to me, that was like a door opening, and it made me realize that if you work hard enough and if you develop enough skill and competence, that you can help be part of a group of people that make impossible things happen. And so, even though I knew it was an immense long shot, I decided that night that that's what I want to do, and that's why I went to the 4 different universities and why I became a test pilot and did all the other things that I did. It was always within the back of my mind that maybe, just maybe someday, in addition to all these other things that I'm doing, there may also be the opportunity to fly in space.
Okay, well, sometimes young kids email me and they say, well, what are the concrete steps that you have to take to become an astronaut? You have to get a college degree? Do you have to write to NASA? Do you have to be a scientist already? You have to be a jet pilot? I mean, how do you do it? Do you write a letter to NASA? What's the process?
Yeah, it's 3 main things, Michio, for anybody who's interested in someday flying in space. Number 1 is you need a healthy body, just because it's such a demanding physical job, and it lasts a long time. So you need, before anyone's going to sign you up to be an astronaut, they want to make sure that you're going to stay healthy through the duration of your career. So if you're thinking of it, number 1, it's something completely personal, and that is take care of your body, exercise a little bit, eat reasonable food. Number 2 is no matter how you want to fly in space, you're going to need to prove that you can learn complicated things. And you don't know what they're going to be. After I was hired as an astronaut, I had to learn to speak Russian and then learn to fly, as you mentioned in the opener, learn to fly as the pilot of a Russian spaceship in Russian. So you want to hire people that have shown a proven ability to learn, and so the way we do that is advanced technical degree. And it does. We've had astronauts who are veterinarians, polymer chemists,
politicians, right?
Engineers, so at least a master's degree or potentially a PhD. And then the third is a proven ability to make good decisions. So not just a healthy student, but someone who's gone out and worked and managed programs or become a pilot or a deep sea diver or a medical doctor or something where you can show that you can repeatedly make good decisions when the consequences matter. Those are the three, if you're building a little step stool of how to get yourself noticed by a space agency, health, education, and proven decision-making ability, that's kind of the three main legs of it. And then once you have all that, then you can start writing to NASA or SpaceX or whatever space agency and say, hey, this is who I am, these are my qualifications. And then every so often, NASA will hire a new class of astronauts. They're hiring a new class right now, but 18,000 people applied for probably 8 or 10 positions, so it's still intensely competitive.
Okay. Now, let me ask you a question, because on your third space mission, you actually commanded the Soyuz spacecraft, and you speak Russian. So let me ask you a question. What are the differences between being an astronaut and a cosmonaut? Are there any differences at all? What are the differences in the hardware and the training? And what are your basic thoughts?
Well, the fundamental difference is really just language. Cosmonaut, it's the Russian word for astronaut. Cosmos and astro or space, it's just a linguistic thing. In France, they're spationaut, and in China, there's something else, of course, in Chinese language. So it's just, it's mostly a linguistic thing. The actual job is very similar, no matter who you're flying with. It's focus on understanding the equipment. Like, as you say, I was the pilot of a Russian Soyuz and then commander of the International Space Station. And it's an overwhelmingly complex technical job to understand those vehicles. They're the most complex vehicles we've ever built. The International Space Station, the Space Shuttle, hugely technically daunting. And so a large part of an astronaut's job, no matter whether you're doing it in Russian or Chinese or English, is the years of in-depth study of orbital mechanics and control theory, and then how the vehicle works, and then how the vehicle fails, and then how to do all those responses to deal with emergencies and malfunctions individually, and then starting to work with a crew, and then working with mission control to be able to do the whole thing as an integrated group. It is more in depth than almost anybody imagines, and if you're traveling to study on a Soyuz, of course, then most of that training takes place somewhere else. So it's maybe not like most people picture what the job looks like. It is a lifetime commitment, but it's also fascinating and so much fun. And to be able to then do something that was otherwise impossible, to overcome that challenge, that's kind of one of the main benefits and thrills of being an astronaut.
Okay, now let's talk about the mundane, ordinary things of being an astronaut. People ask the question, especially school kids, ask the question of, well, how do you take a shower in outer space, given the fact that water does not tumble down like it usually does, because there's, of course, weightlessness in outer space. So how do you do mundane things like take a shower?
Well, the easy answer, Michio, is you don't. For 6 months, you don't take a shower. And, of course, you can't fill a bathtub with water when you're weightless. And we tried building showers, but without gravity to pull the water down into a drain, it just doesn't work. You just end up with a thick, kind of clinging coat of dirty water on your body that you have to vacuum off, and it's very water wasteful. So we just take sponge baths, just sort of like a patient in a hospital. Just a little bit of cloth, wet cloth, get yourself wet, a tiny bit of lather, then clean yourself off with another wet cloth, and then just let that cloth evaporate back in so we can reclaim all of the water in the water cycle on the spaceship. And we reclaim about 92% of all the water on the International Space Station. So you're washing your hair, you just use this special type of shampoo that doesn't use any water. You just squirt it in your hair, lather it up, dry it on a towel, and the oil comes out of your hair onto the towel. Shaving, you just wipe it on a cloth. Brushing your teeth, you just swallow the toothpaste. I mean, everything is super water careful, and it works okay. I mean, in 6 months on the space station, we were all clean and healthy and fine. It's just a little different set of rules than down here on the surface.
Okay, and how do you eat in outer space? First of all, in science fiction movies, the astronauts always grimace when they see the prepackaged synthetic food they're given, and of course they have to slurp the food because it would float. But, well, you're a real astronaut. How do you eat in outer space?
It's a lot better, I think, than traditionally shown in the movies. But if you think about it, of course, the delivery train to try and get your food up to the spaceship is pretty lengthy. And once it's on board, it's not going to be immediately consumed. It's not like you're going to have much fresh food at all. And in fact, because of the complexity, we don't have normal cooking equipment on board. We don't have an oven, we don't have a stove, we don't even have a microwave, and we don't really have refrigerators or freezers for our food. So everything is the type of food that could be in a dry pantry. And
okay, Chris,
so
we have to take a short commercial break, and after the break, we're going to continue a discussion with Chris Hadfield, astronaut. We're talking about Mars and the conquering of outer space.
You're listening to Science Fantastic with Professor Michio Kaku. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're going to blast off to Mars with our special guest today, astronaut Chris Hadfield. Well, let's just jump right into where we were off. We were talking about a day in the life of an astronaut. And so let's talk about being an astronaut in outer space. First of all, when you look down at the planet Earth, you see the planet Earth whole without political boundaries, and it seems so peaceful. But do you sometimes get this disconnect given the fact that we have all these political problems and droughts and catastrophes and revolutions, and there you are in outer space looking down on the planet Earth. So what's it like to look at all of humanity in 90 minutes as you go around the planet Earth?
I think, Michio, it's the people on the surface that get more disconnected because they get so wrapped up in local events, they forget that the rest of the world exists. And so you tend to think that your street or your suburb or your town or whatever, that's the only real one that counts or matters. Whereas on board a spaceship, you go around the entire world 16 times a day. You see the entire planet constantly, and everybody on it, all 7.5 billion people. And you get a real sense of the shared nature of it and the fact that we're all in this together, and a constant, unfiltered visual reminder of where we all live, and the fact that that so much of our poor decision-making is because people only think locally. So I really think the perspective we get from a spaceship is a really key one for us to make good decisions, and also for the inherent survival of our species and the planet itself.
Now let's talk about the dangers, the downside of being an astronaut. First of all, radiation. You are way above most of the atmosphere, and I understand that you can actually see cosmic ray flashes in your eyeball. Could you elaborate?
You're right. Of course, the particles of the atmosphere and the water vapor, the stuff that makes clouds in the atmosphere, it soaks up so much of the radiation that comes from our sun and that comes from all the other stars of the universe, so that we're kind of under a beautiful radiation shield down here at near sea level. The higher you go, the less protection you get. And on board the spaceship, as you say, we're pretty much above all of the atmosphere. So if you close your eyes on a spaceship, amazingly enough, every so often you see a flash of light. And what it is a high energy atomic-sized particle going through your optic nerve. You can actually see the effect of the radiation going through your body. It's a pretty good reminder that you're not in Kansas anymore. You are somewhere else. But it's going to be even worse when we go further away, because even at the height of the space station, we're still inside a lot of the world's magnetic field. And that magnetic field is another form of radiation protection. When we decide to venture further, we're going to have to design spaceships that somehow take the place of the magnetic field and the Earth's atmosphere, where we've evolved under their protection.
Okay, and also micrometeorites, given the fact that empty space is not really totally empty. So have you had any discussions or realizations, the fact that space is potentially dangerous?
Oh, it's funny that you say micrometeorites. We're more concerned about the macro meteorites than the the big ones. The space station gets sandblasted by little tiny particles all the time, and if you just sit quiet for a minute, you can hear them hit the space station like a little ricochet, because you're out in the openness of space, and the Earth gets hit by 50 tons of meteorites every day. 50 tons a day hit the Earth, and every ounce of that comes through the orbit of the space station, of course. So some small percentage of them hit the space station. And so that's a definite risk. There is the risk that one of the pieces will be big enough that our armor won't protect. We have a tiny little bit of armor on the station, but we worry about it, and we practice in case you have a hole punched in to deal with loss of pressure and depressurization. It's one of the risks that astronauts face.
Okay, let's take another short commercial break. Once again, you are listening to Science Fantastic with Professor Michio Kaku. When we come back, we'll talk about Mars. What is it like to spend 2 years in outer space going to the red planet?
This is Science Fantastic. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, our special guest today is Chris Hadfield. He's been shot into outer space as an astronaut 3 times, once as the commander of the International Space Station and also a Soyuz Russian spacecraft. Well, President Barack Obama made history recently by stating flatly that the next mission is to Mars. NASA has been criticized as being the agency to nowhere, but now it's going to go somewhere. It's going to bypass the moon and on to Mars, perhaps in the 2030s. Of course, the mission is going to be quite potentially dangerous. First of all, the journey could take 2 years, 9 months to get there, several months to do your scientific experiments on Mars, and another 9 months to go back. So, Chris, tell us about that. Given the fact that the world's record for being in outer space continually is just a little bit more than just 1 year, what are your thoughts about sending an astronaut 9 months to the red planet and 9 months back? What are your thoughts?
Well, the real question, Michio, is why are we going? What is the purpose in going there? I mean, is it just to show that we can, or is it to try and understand Mars, or is it to start settling there, like we have slowly expanded and settled all over the surface of the Earth? I think that really determines when we're going to go and how urgently we should be working on it and how long it's going to take. And when you say 9 months, you're of course assuming some particular level of rockets and speed and all the rest of that. And there's lots of different technologies out there. So it's easy for the president to say 20 years in the future, of course, because that's just a good goal and inspiring people. But the actual practicality of how it's going to unroll, it'll be interesting to see. But we're all going to spend 9 months somewhere, or 6 months somewhere, or whatever. It's not that crazy or different to think that you might spend 6 months or 9 months on board a spaceship. We're all going to be on board something for that period of time. You just need to choose the right people. You need to give them the right training. You need to give them the right purpose, so that they feel that their time is valuable and what they're doing is worthwhile, and then give them a reasonable level of expectation of success and safety, that they know it's not going to kill them in the process. And I think with that combination, there will be an unlimited number of people that'll be volunteering to go. And I don't know how you would feel, but I would love the opportunity.
Okay, now let me ask you about the psychology of being cooped up in a space station or in a capsule going to Mars. There's, of course, no psychological, or maybe there are. Let me ask you that question. Is there a psychological matching of astronauts? Because what happens if you're matched with an astronaut that gets on your nerves? There you are, stuck with this astronaut for maybe 2 years, and he, eats crackers in bed or snores, or something happens that grates on your nerves. What happens then? Because you're cooped up for a long period of time. Any thoughts?
Well, cooped up, a lot of people feel cooped up in the middle of New York. or they, cooped up is a mental thing. If you have the entire universe in your window and you're on your way to a new planet, you could look at that as the ultimate freedom. It's kind of a personal decision. And then for crew selection, they don't just choose us and then, throw us together on a spaceship where we meet or something. The selection to choose astronauts tries to choose people with the right natural psychology. And then you're selected years and years in advance of the time you would go because the training is so intensive. And so you'll train with your crew probably for 5 years before you go to space. So there's a huge amount of time to develop all of the interpersonal skills needed in order to successfully do a mission like that. And so you definitely you treat the psychology just as seriously as you treat the technology and the science on board.
Okay, let's take another short commercial break. Once again, you are listening to Science Fantastic.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. In this segment, we're talking about Mars and the exploration of outer space with Chris Hadfield. You've been probably following the headlines. First of all, Elon Musk, the head of SpaceX, founder of PayPal and Tesla Motors, has announced that, yes, he is sending his fleet of ships to Mars. By 2024, he wants the first unmanned Falcon X SpaceX rocket to go to Mars. And then after that, he wants to send a piloted mission to Mars. And after that, he envisions 1,000 rockets being sent to Mars, each one with 100 colonists to create the first city on Mars. Of course, that goal is many, many decades away, but he's laid it out. 1 million inhabitants on the first city to Mars. And then Boeing Aircraft jumped into it and said, now, wait a minute, we don't want Elon Musk to get all the headlines. Boeing is now in the race to field rockets to go to Mars. And then NASA is now jumped in. President Barack Obama has stated that, yes, then the U.S. is now backing a space mission with the SLS booster rocket. One of the largest booster rockets ever constructed, the SLS, is now undergoing trials. So it looks as if Mars is the way to go. But there's also a movie out there with Matt Damon. So, Chris, you were there at the opening of the movie, The Martian. What are your thoughts about the accuracy and the impact of the movie, The Martian?
The movie is one of the best space movies recently done, I think, for a couple of different reasons. Number one, it's based on a terrific book, The Martian by Andy Weir. Andy worked so hard to try and make it as real as he could, to make the characters be representative of what a real astronaut would do and say, and to try and get the technology right. He had to make a few things a little more dramatic to tell a story, but he did a really nice job. And then in the movie, they reflected that pretty well. The way that Matt Damon portrays the lone guy on Mars, Mark Watney, Matt Damon, that character could have been anybody in the astronaut office. That's just the type of people that NASA and the space agencies attract, and he would have fit right in. And the storyline was pretty good. They had to simplify it all down to 2 hours. So you have to make a few things unrealistic to tell a whole story. But to try and capture people's imaginations, to give them a sense of what it might be like to see some of the huge scientific and technical challenges and skills that are needed, and then to show some of the things that go wrong, I think it was a really good adventure. I enjoyed the book and the movie very much.
Okay, now on the movie, some people claim that when you go to Mars, you can live off the land like our pioneers. Our pioneers didn't have to bring water and soil with them. No, they simply grew crops. However, on Mars, there's a scene where Matt Damon has to confront the fact he's running out of food, running out of oxygen, and he has to use his own waste products to fertilize crops. So tell us about this. You can't really live off the land on Mars, right? There's no soil, air to speak of.
Well, it depends how you define living off the land. If you can build a structure that can keep a bubble of air inside it, then inside that bubble you can live off the land. It's harder than, of course, on Earth. The atmosphere is so thin on Mars that we would die within a few minutes if we were completely unprotected. But there's places on Earth that are that way, deep in the ocean, high in the Arctic, down in Antarctic. There's parts of the world that are pretty uninhabitable, too. The real question is, how much technology can you bring with you? And can that then set up a little bubble that would make living off the land possible? And where you're getting your electricity from. But if you can fundamentally have a place with a power source and a bubble of habitability, then yeah, we can be living on Mars. We have to fit it into everything else that's going on in society, decide why that particular exploration is important, just like the exploration that goes on all around the surface of the world. But I really think we will go from the space station to the moon to Mars, just as the natural extension of the human exploration that's been going on for the last million years.
Okay, now in the movie The Martian, of course, they had a tiny space station on the surface of Mars. Some people are saying, well, the surface of Mars is so potentially radioactive and dangerous with micrometeorites and stuff that they should go underground, that they should dig a hole and live underground, protecting themselves against the deadly radiation from the sun. So perhaps the movie was a little bit ahead of its time. But, well, what are your thoughts about a day in the life of an astronaut walking on the surface of Mars where it's cold, it's below freezing, there's no air, as you pointed out, and it's quite brutal?
Yeah, it sure is not going to be the life that most of us are used to here on the surface of the Earth. But if you compare it to the demands of life of some people's careers, like if you're a deep-sea fisherman and you're out in the wilds of the North Pacific, or if you're a researcher who lives at the South Pole, or one of the more extreme parts of the world, you make a lot of compromises in normal comfort to enable the ability to do your job. And Mars will just be the most extreme example of that. Like the people that are up on the International Space Station right now, it's a very hostile environment. You can't survive more than a few seconds, really, outside the ship. But in the inside, you can be hugely productive. And Mars will be somewhere in between that type of existence and the normal one we're used to. And it seems fanciful. It seems crazy, Michio, but compare it to the fact that when I was born, no one had ever even flown in space. In your lifetime, my lifetime, all of human spaceflight has occurred. And we've had people living on the space station for 16 years. So it may seem crazy and fanciful, but in reality, it's just one small step after another that leads us into doing things that were otherwise impossible.
Okay, well, unfortunately, we've run out of time. So, Chris, thank you so much for being on Science Fantastic.
Nice to join you. Thanks a lot, Professor.
This is Science Fantastic with Professor Michio Kaku. And in this hour, we're going to throw the lines open because this hour is your hour. Let's take the first listener phone call.
Dr. Kaku, this is Mike at KONA Radio in Kennewick, Washington, calling. And my question is this. I recently purchased for my stereo system a vacuum tube amplifier. Can you tell me how a vacuum tube amplifier operates differently and processes sound differently than from a transistor or solid-state radio? Thank you, Doctor.
Well, you ask a very interesting question. When I was a kid, I remember that our TV set had a lot of vacuum tubes in it, and every time it blew out, I would go to the store, have to bring in each tube and test each tube with a vacuum tube tester at the supermarket. Well, those days are gone because everything, of course, is now transistorized, and you can't simply test each transistor because there are literally millions of them inside your TV set. So what's the difference? A vacuum tube and a transistor share one basic feature, and that is they are gates. Gates which control the flow of electricity. Now, if you have like a river, and the river is quite large, very, very strong river, but you have a gate that is controlled by your fingertip, just by your fingertip, let's say, then your fingertip can actually control the flow of a mighty river. Well, that mighty river is the flow of electrons inside your TV set or whatever. And that finger that allows you to control the gate is called the transistor. And the whole process by which a small little impulse from your finger controls the flow of a mighty river, turning it on or off, is called amplification. That's how you have amplifiers. And so to summarize, a transistor and a vacuum tube are nothing but gates which control the flow of electricity, allowing a small amount of electricity to control the flow of a much larger amount of electricity, and that is what an amplifier is. Now, if the two are basically the same, that is, they're both gates, what is the superiority over one over the other? Well, a transistor is superior to a vacuum tube because you can miniaturize it. You can put literally millions, hundreds of millions of transistors on a silicon wafer the size of your thumb, and yet a vacuum tube was the size of your finger. And so you immediately see the advantage of going from vacuum tubes to transistors. You can control the flow of electricity with a very, very tiny set of transistors. You can you can control the flow reliably, because vacuum tubes would blow out. That's why I would have to go to the supermarket every few months and replace the vacuum tubes that continually blew out. So you see that you can pack more transistors. Transistors are more reliable. They use less electricity, so you don't heat up the back of your TV set like with the old vacuum tubes. So you can see the enormous amount of advantages that transistors have over vacuum tubes. However, there's kind of like an anecdote to this. Years ago, it turns out that a Russian pilot defected, and he flew the Foxbat, a very advanced MiG jet fighter, to the Allies. Now, the CIA was extremely interested in this because this was the state-of-the-art Russian aircraft that was commandeered by a defector, flown to the West. Well, of course, the CIA took that Russian jet fighter piece by piece, and they were shocked, absolutely shocked. There are books that reference this, in fact. They found a lot of that, the vacuum tube, a lot of the technology that the Russians were using back then was vacuum tube technology, not transistorized technology. So on one hand, the CIA was laughing their heads off, saying, ha, we're way ahead of the Russians. But then some people said, uh-oh, maybe there's a reason why they use some vacuum technology, because if you have an electromagnetic pulse created by, let's say, a hydrogen bomb, you can wipe out the electronics in an advanced jet fighter, but vacuum tubes are more resistant to electromagnetic pulses than transistors are. And so all of a sudden the CIA said, uh-oh, maybe there's a rhyme to the reason. Maybe they are sly as a fox, that the Foxbat uses ancient technology because they actually want to create a jet fighter that is relatively invulnerable to a space-age threat, the electromagnetic pulse. Well, I think anyone that looked at this objectively would think that maybe the CIA overreacted a bit. Transistor technology is so much superior to vacuum tube technology. Okay, well, moving right along, let's go to the next listener phone call.
Hi, my name is Mary. I'm from Arkansas, and I have a question about the brain. They say we only use 10% of our brain. So we have that other 90%. And they also say that we stop forming brain cells. And I was wondering that, and it controls like our muscles. Like you were saying about a violin, the structure in the hand. It shifted in the form of the blood vessels and, you know, the cells and all of that. So I was wondering, you know, if there's a way that we could actually practice being able to use areas of our mind and be able to, you know, enhance ourselves. And I want to say I appreciate you very much. You inspire me, and I love your personality, the way you teach. You have a really good way. You're very ambitious, and I appreciate that very much. Bye.
Well, thank you very much. And first of all, let me correct something. There's a very common myth enshrined in the movies, in fact. There's a movie called Lucy, which is based on the idea that we only lose 10% of our brain power. That's actually not right. In fact, some scientists have tried to track down where that piece of misinformation first came from, and apparently it came from a comic book. I remember reading the comic books in the old days where they would have a page of facts. A lot of the facts, of course, were probably incorrect or misinterpreted, but one of the facts in this comic book was that we only use 10% of our brain. Actually, with brain scans, we can measure the neural activity of the brain, and we find that the conscious brain is actually rather small, probably less than 10%. Most of the brain is unconscious because it has to regulate breathing, heart rate, sensations. Most of the time, you're not even aware of what your brain is doing. So, yes, we use all of our brain, but the conscious brain is actually in the prefrontal cortex right behind your forehead, and that is where your conscious brain is located, and only a tiny fraction of your brain power goes into the conscious brain. Now, of course, you're asking a different question, and that's the question of enhancement. Well, our brain is not a computer. A computer has, of course, software. It has a Pentium chip. It has Microsoft Word, operating systems from Microsoft or whatever. No, our human brain has none of those things. There's no CPU, there's no Pentium chip, there's no Windows software at all. Our brain is a learning machine. It rewires itself after learning every task, while your laptop today is just as stupid as it was yesterday. Your laptop never learns because it is what is called a Turing machine. That is a glorified adding machine. So enhancement is possible with the learning machine. In fact, the basic way in which our brain learns is through something called Hebb's rule. Hebb was a neurologist who stated that the more you use a neural circuit, the better you get at it. You learn as a process. In other words, how do you go to Carnegie Hall if you're a musician? The answer, practice, practice, practice. And that is absolutely true. If you want to enhance a certain aspect of your abilities, just practice, practice, practice. That's Hebb's rule, because the brain rewires itself after learning every single task. In fact, there's something called the 10,000 hour rule. If you take a look at professional musicians, prodigies, people who are concert pianists and stuff, and you calculate how many hours they spent doing it, it was about 10,000 hours when they were a kid. So you see that, yes, even concert pianists obey this rule. The more you practice, the better you get.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Okay, well, moving right along, let's take the next listener phone call.
Hello, this is Armand from Bayside, Queens. And I was wondering if one could hook up their mind to a machine and have that machine read their thoughts and project it onto a movie screen or a 3D camera system. So pretty much you're projecting your ideas into reality. Would that be a possibility one day? Thank you very much for your time and have a great day.
Well, as preposterous as that may sound, the answer to your question is yes. In fact, we can even do a primitive version of that right now. We're not talking about waiting 100 years into the future. This is done at Berkeley, the University of California, where I got my PhD years ago. And here's how you do it. You put the thinking brain in an MRI machine, and the person is asked to concentrate on a picture. The picture they use, for example, is the Mona Lisa. Then the MRI machine scans the living brain and divides the brain into 30,000 dots. Each dot represents blood flow in that particular part of the brain. You can do that with MRI machines because they analyze oxygen content in the brain, which corresponds to the flow of blood, which in turn corresponds to the flow of electricity in the brain. So you now have this picture of the brain with 30,000 pixels. Then you put it into a computer. A computer scans all 30,000 dots, and then has a software program that analyzes it and then prints out a picture of the Mona Lisa. Now, the picture is not precise. In fact, you can Google it and actually see these pictures for yourself, but it is a reasonable facsimile based on only 30,000 pixels of the Mona Lisa. And when you go to sleep, the machine just keeps on chugging away and prints out a reasonable facsimile of things that you are dreaming about. And so, yes, it is possible to actually extract pictures from the living brain. The pictures are kind of crude. I'll be the first to admit that. But the fact that we can even talk about this at all is astounding, because most people would think that human thought is beyond our capabilities and the capabilities of science. So it's amazing what we can do. In fact, I was on a science program on the Science Channel called Futurescape, where we actually showed these pictures on national television. Amazing. Okay, well, let's move right along to the next listener phone call.
Hi, yes, my name is Robert, calling from WCHS in Charleston, West Virginia. The proof is not in the pudding, as the old saying goes. The proof of the pudding is in the eating. Since you're the master of string theory, the theory of everything, my question is twofold. What do you hope to accomplish with this? And if you do succeed, in what way or ways will it benefit society? Thank you very much.
Well, you asked a very interesting question. First of all, there's even a Hollywood movie which won the Oscars about a theory of everything. It's about the life of Stephen Hawking. However, I watched the movie, and I noticed they never mentioned the name of the theory. So there you are, sitting 2 hours through a movie about the theory of everything, but they don't tell you the name of the theory. The name of the theory is string theory, and that's what I do for a living. In fact, I'm the founder of string field theory, which allows you to summarize all of string theory into an equation no more than about 1 inch long. So this theory contains all known physical laws. That is, general relativity, the black holes, exploding stars, the Big Bang, all included in the theory, plus electronics, lasers, your iPad, your iPads, and radios and television, all the electronic wonders in your living room are also included as solutions of this theory. And so then the question is, well, A, how come we don't win the Nobel Prize for it? And B, so what? Well, to answer your first question, that is, why don't we get recognized and win the Nobel Prize for this theory? And the answer is very simple. You have to test it. And it's very difficult to test because you have to have an atom smasher even bigger than the Large Hadron Collider. And it would be very expensive to test this theory. And so let's take a short commercial break. But after the break, we'll try to answer the question, how do you test the theory of everything? And what can you do once you have a theory of everything?
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Well, once again on Science Fantastic, we're throwing the lines open because this hour is your hour. Okay, first of all, I neglected to finish answering the previous question, so let me do that. First of all, once we have a theory of everything, a theory that can explain the Big Bang and subatomic particles and transistors and radios and the Internet. Once we have such a theory, what do we do with it? Well, in the short term, we're not going to do anything at all because it's a theory of the universe. And to test it, you have to literally create an entire universe in a laboratory. But once you have such a theory, we can then begin to answer questions that even philosophers have asked about. Time travel, for example. Time travel is allowed in Einstein's equations, but we don't know how stable a time machine is. Perhaps it'll blow up when you enter it. String theory will answer that question because it doesn't blow up. It's a finite theory. So we'll be able to answer the question about whether or not you can bend time into a pretzel. Also, gateways to other stars. It takes thousands of years to reach nearby stars, so why not take a shortcut by building warp drive engines? Well, is that just science fiction? Within Einstein's theory, well, you can't resolve the question because Einstein's theory does allow for wormholes, but it doesn't say how stable they are. String theory will answer that question. Also, what happened before the Big Bang? We know very little about the Big Bang. We know that it banged. We know we don't know why it banged or why it banged in that particular way. We don't know, therefore, why the universe came out the way we did, or whether other possible Big Bangs can happen. We know nothing about that. And so string theory should be able to answer that question. What happened before creation? Why are we here even talking about that question? And why did we emerge from the Big Bang the way we actually did? So moving right along now, let's take the next listener phone call.
I would like to know about Planet X. I have quite a few questions about Planet X. And its 180-day orbit. It's due back into our vision again in November. What do you know about Planet X?
First of all, I get a lot of emails about Planet X or Nibiru. Some people think that there's a gigantic planet out there that's going to come barreling down our solar system and perhaps hit the Earth and wipe us out. A lot of doomsday scenarios are therefore linked with Planet X. Well, let me say right now that I've had astronomers on Science Fantastic. They've scanned the solar system, and they see no evidence of a Planet X that's going to come barreling down our way and strike us. There's no doomsday planet out there that we can see with our telescopes. However, our telescopes have revealed new objects out there that caught astronomers by surprise. First of all, there are more dwarf planets, that is, objects that are about the size of Pluto, a dwarf planet, and mainly made out of ice. And yeah, we've noticed several of them outside the orbit of Pluto. And second of all, just recently, some scientists at Caltech, using computer simulations, have said that, yeah, there does seem to be a giant planet out there perturbing the orbits of the inner planets. It's not Planet X. It's way out there. And we're still debating its characteristics. So the short story is, there's no Planet X that's going to hit the Earth anytime soon. The orbits of these objects that I mentioned have period time measured in centuries to thousands of years, and most of them are tiny, and they're in orbits that are not going to intersect with the planet Earth. There is a wild card. There's a new planet out there discovered by Caltech astronomers. However, again, we don't think it's going to hit the Earth anytime soon, so personally, I wouldn't worry about it. Okay, well, moving right along, let's take the next listener phone call.
Hello, Professor. My name is Scott from College Station, Texas. And I was wondering, I heard you speak previously about multiple dimensions in some of your research, and was wondering how you tied in evolution and the theory of how some things may come out of nothing, paralleling with all other dimensions as well. Thank you.
Okay, well, let me try to answer that question. First of all, one reason why string theory, which is what I do for a living, is not immediately universally accepted by scientists is because it predicts the existence of other dimensions that cannot be measured using ordinary technology. Now, these other dimensions, think about it for a moment, might exist because why do we live in a three-dimensional universe? We know that objects can be described by length, width, and height. That is, three numbers, length, width, and height, describes any object in our universe. And given a fourth number, that is time, we can now describe any event in the universe. For example, if you want to meet somebody in Manhattan, you say, meet me at noontime at the corner of 42nd and 5th Avenue on the 10th floor. So with four numbers, you can typify any event in the universe. But string theory is a mathematical theory. It says that we live in an 11-dimensional universe, and that freaks people out. So after the break, we'll talk about higher dimensions and whether or not they actually exist.
This is Science Fantastic. You're listening to Science Fantastic with Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. This hour is your hour. Well, before the break, we had another call who talked about higher dimensions. Yes, I work on something called string theory. Yes, we think it goes beyond Einstein. We think it is the theory of everything, which was the basis of a Hollywood movie starring Stephen Hawking. And then the question is, well, what's wrong with the theory of everything? Why don't we recognize that it is the theory of everything? One thing that puzzles many physicists is that it predicts that the universe has more than 3 dimensions. There are other universes out there. And that upsets some people, quite frankly. However, it does seem to fit the data. We realize, for example, when you look at the Big Bang, the largest atom smasher of all is the creation of the universe. And when you look at the Big Bang very carefully and analyze the data, you realize that it seems to be a theory which fits the predictions of inflation. That is a very rapid expansion of the universe. But inflation theory predicts that it can happen again and again and again. So that our universe is a bubble that can peel off other baby universes. A bubble that can actually collide with other universes, giving birth to yet more universes. And we call that theory the multiverse. And so string theory gives you a bizarre prediction, a prediction that perhaps we coexist with other universes, that Big Bangs happen all the time, like in a bubble bath. So think of a bubble bath, and our universe is nothing but one bubble among a bubble bath of universes. Now, of course, to prove the theory is quite difficult. We want to have satellites like LISA, the Laser Interferometry Space Antenna, that may give us clues as to the universe before the Big Bang. Now, of course, LISA has been delayed. It means that we're going to have to wait until we can actually do this. But yes, it's testable, a testable idea that perhaps there are other universes using the Big Bang itself as an atom smasher in order to probe the deepest secrets of space and time. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. Okay, once again, let's continue our discussion, and let's have the next listener phone call.
Hi there, my name is Barry, and I just heard your theory, I guess, that the universe is expanding, and that if we're going to get cold because we don't have any light, do we get light from the other galaxies, or do we just see the other galaxies? I mean, don't we get our light from the sun? Is the sun going to pull away from the rest of the solar system? Of course, then there wouldn't be a solar system, would there be? I just don't understand what you're trying to say, and it doesn't sound valid. Help me out.
Okay, well, you ask a very interesting question about the end of the universe. Now, Einstein's theory predicts that there was an explosion which created everything you see around you. However, Einstein's equations keep on going. They don't stop. They keep on going into the future, billions, trillions of years into the future. After an unimaginable amount of time of an expanding universe, the galaxies are so distant and stars have died out that the universe becomes totally black as a consequence. We're still in the era where we still have stars that light up the universe, but stars themselves don't last that long. Our sun, for example, is middle-aged. It's about 4.5 billion years old. It'll have a total lifespan of maybe 10 billion years, so it's middle-aged. And over a trillion-year process, we're talking about even small dwarf stars, which live longer, eventually blinking out. And then over a period of maybe 100 billion years, we'll have a universe full of dead stars, neutron stars, and black holes. And then even beyond that, trillions upon trillions of years, even the black holes will exhaust their energy. And by that time, the universe will be so big and the stars will be so old that the universe will become black. And it'll be very cold as a consequence. Things will freeze to death. Temperatures will reach absolute zero, which is the absolute lowest temperature you possibly can have, where even machines cannot function. Cells, life, machines, everything we know it ceases to move at that point. My point of view is that once we reach that point of the big freeze, we should perhaps leave the universe. Leave the universe because there perhaps are neighboring universes which are younger and warmer. And, of course, this borders on science fiction, but it is within the laws of physics that one day, perhaps trillions of years into the future, our descendants may simply give up on our universe, leave our universe in a dimensional lifeboat, which I describe in my book, Parallel Worlds, by the way, if you want to see a description of this machine, and go to another universe which is warmer, and then we can begin the process of messing up that universe as well. Okay, well, let's move right along to the next listener phone call.
Hello, my name is Paul Dans, and I'm calling from Claremont, New Hampshire, station NTK. And my question for you, sir, is it possible that we might be able to develop a vaccination against addiction? Thank you.
Okay, well, the short answer to that is there's no vaccine in sight for addiction. If you get my latest book, The Future of the Mind, I actually talk about addiction and how is it that certain chemicals can hijack our dopamine cycles, and that's how addiction works. Addiction is involved with the chemical dopamine, which is released when you, quote, get high. And at the present time, we have no immediate way of dealing with it. First of all, vaccines are good against germs, like, let's say, viruses. The body creates its own antibodies over, of course, millions of years. And by stimulating these antibodies, you can get the body to fight these germs. However, the drugs are synthetic. We're not talking about ancient diseases that have existed with nature for millions of years, for which evolution gives us defense mechanisms. No, these chemicals are artificial. They hijack the pleasure centers. They hijack the dopamine cycles. And that's what causes addiction, which is a modern-day phenomenon. In fact, if you get, for example, rats hooked on alcohol, yes, you could have alcoholic rats. You can actually get animals addicted to these chemicals because these chemicals, by and large, are synthetic, that is involved in addiction. And so I discuss addiction, what is known about it, but at the present time, we have no way of being able to dampen the fires of addiction because addiction actually hijacks some of the biological mechanisms of the body, especially those chemicals that are involved in the pleasure cycle.
Now, Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Okay, well, moving right along, let's take the next listener phone call.
Yeah, listening from Northeast Pennsylvania, WILK, and the sun will interest me the most. How it keeps, where the energy comes from, how it keeps shining, the diameter, and if it shines on the backside also. Thank you very much. Bye-bye.
Okay, well, the sun does not shine on the backside. It shines uniformly throughout the entire sphere, and it does so because of a process called fusion. In other words, hydrogen gas, which is what the sun is basically made out of, is compressed evenly on all sides by gravity, and as it compresses, it heats up in temperature, just like the opposite of your refrigerator. When you expand the gas inside the coils of your refrigerator, it gets cold. When you compress gas, it gets hot. So that's what happens to the sun. Gravitational pull turns gravitational energy into heat. When you hit several tens of millions of degrees at the center of the star, protons are slammed into protons and hydrogen, creating helium. And so the fusing of hydrogen into helium creates energy via E equals mc squared. So M is a tiny bit of hydrogen which turns into energy. E is energy. And c is the speed of light squared, which is a humongous number. That's why even a tiny bit of uranium will unleash the atomic bomb. So a piece of the sun, no more than a teaspoon, has enough energy in it to devastate all of New York City. That's the power of the sun. Now, if you were to think that the sun shines because of oil or coal, you would have a problem. First of all, there's no air out there, so there's no oxidation of coal or oil to heat up the sun. And second of all, you can also show that even if there was oxygen out there, it would be exhausted in a matter of just a few hundreds or a few thousands of years. And yet the sun has been burning for 4 to 5 billion years. And so a new force is involved, not the force of fire, but the force of nuclear fire. And that force is unleashed by Einstein's E equals mc squared. Okay, well, let's move right along to the next question.
Hi, Dr. Kaku. This is Peter Kleiman. Glad to talk to you again. Once again, I just had a question on physics. My question is, why is the speed of light not something faster or slower? Why is c the number, the value that it is? Is it different in other universes? Is it the same across the whole entire multiverse? Why is it a certain value? Thank you for letting me ask a question. Thanks. Bye.
Well, you ask a question which is quite embarrassing for physicists. The short answer is we don't really know. Einstein simply starts with the speed of light being what it is, and then he probes the consequences of that fact. But then you can run the videotape backwards and say, now wait a minute, where did that first assumption come from? Where did the speed of light itself comes from? And the answer is we don't really know. However, in our universe, we think that the speed of light is a constant, just the way Einstein predicted. When we look at radiation, light radiation coming from the distant galaxies at the very edge of the visible universe, we find that the laws of physics and the laws of optics are the same, exactly the same. We don't see any difference at all. So this distant galaxy could be next door, and the radiation that we get from them would be very similar. And so we see no change in the laws of physics in this universe. However, you ask another question, and that is there a multiverse of universes? And in these other universes, can the speed of light be different? And the answer to that is, well, maybe. First of all, I work on something called string theory, which we think is a successor to Einstein's theory of gravity. We think it is the leading candidate for a theory of everything. In fact, if you saw that Oscar-winning movie, The Theory of Everything, the one problem with that movie is they never told you what the name of the theory is. They simply talked about Stephen Hawking's life and his ailment. Well, the theory is called string theory, and that's what I do for a living. And string theory says that our universe is a bubble floating in a much larger arena of hyperspace, in fact, 11-dimensional hyperspace, but there could be other bubbles out there that once in a while bump into our universe. Now, when these universes bump into each other or fission off and peel off a baby universe, the laws of physics can change. And so we have a multiverse of universes such that each universe has its own string theory. In other words, the different constants of nature, including the mass of the electron, the speed of light, things like that, may actually be different. The laws of physics may actually be different in these other universes. Now, can we prove it? Well, the Europeans think we might be able to have a handle on this question. They plan to launch LISA into orbit in the next 20 years. LISA is the Laser Interferometry Space Antenna. It is designed to pick up gravity waves not on the Earth. We've done that just a few months ago, gravity waves on the Earth, but gravity waves in outer space. Gravity waves emitted not from colliding black holes. We did that just a few months ago. But gravity waves from the creation of the universe itself. And that should give us radiation from the pre-Big Bang universe. And then we can have numbers, real measurable numbers, to answer the question, are there different laws of physics in other universes? So the short answer to your question is we don't know, but it is room for experiment. And the European Space Agency will send satellites into outer space to measure gravity waves from the Big Bang, and that should give us a clue as to whether or not other universes can exist. And then, of course, everyone wants to ask the last question, is Elvis Presley still alive in another universe? Well, if the speed of light can change in other universes, then, yeah, there's always a chance that the King could be alive in another universe. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. Okay, well, moving right along, let's take the next listener phone call.
Hi, Professor. This is Tony calling from Jasper, Florida. My question is, if two spaceships are moving toward each other at 186,000 miles per second, the speed of light, what is the total impact of the collision? Is it 186,000 miles per second, or is it double? Thank you.
Well, you ask a question that the young Einstein asked himself when he was 16 years old. You see, if the speed of light is a constant, that means that all sorts of bizarre distortions take place. First of all, if you're coming at an object at near the speed of light, and it's coming at you near the speed of light, then common sense tells you that the relative velocity is twice the speed of light. Or let's say you're in a train that's speeding near the speed of light, and you have a flashlight. You light the flashlight in the direction of motion of the train. Since the train is moving at the speed of light, and the light bulb is emitting light at the speed of light, then an outside observer would say that the light beam is moving at twice the speed of light. Wrong. We've done this experiment. It is always according to Einstein's theory. Velocities do not add. That's the simple question. In fact, there's even a mathematical formula that shows that if you're moving at the speed of light or near the speed of light, and you're moving in a train that's moving near the speed of light, the sum of the two is not twice the speed of light. You have to divide by a certain relativistic factor. Now, how is it possible that an object can seemingly have two different velocities depending upon who measures it? And the answer is that a man inside a rocket ship, his brain slows down relative to somebody looking at the rocket ship. So let's say you have a rocket ship traveling near the speed of light, and you turn on a flashlight. By rights, the flashlight should be going at twice the speed of light, but it isn't. It always moves at the speed of light. Now, you may tear your hair out saying, how's that possible? And the answer struck Einstein in a streetcar in the spring of 1905. He was thinking about the clock tower, the famous clock tower in Bern, Switzerland, as the streetcar was leaving, and he asked himself a question. If this streetcar were moving at the speed of light, what would I see when I looked at the clock tower in Bern? Then he got it. He said that a storm broke in my mind. And that is, the person inside the train, his brain slows down because time itself slows down in the rocket ship. Every time he tries to measure things, it always comes out that the speed of light is exactly the same, no matter if the light beam is moving toward you, the light beam is moving away from you, or the light beam is moving at an angle with respect to you. Now, that violates common sense. Everything in your fiber, everything in your experience tells you that velocities add. Well, wrong. The universe does not believe in your common sense. The universe says, nope, that's not true. The speed of light is a constant no matter how you measure it in any frame. And we've done this. Time and time again, we've sent rockets, ships into space, airships. Each time, the speed of light comes out exactly the way Albert Einstein said. In fact, your GPS system in your cell phone, in your pocket, depends on this. If Einstein were wrong, all GPS systems on the Earth would fail, because time does beat at a different rate for GPS satellites orbiting the planet Earth. And so you say to yourself, well, that violates common sense. The answer to that is tough. Sorry about that. The universe does not obey your common sense. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. Okay, well, let's move right along to the next listener phone call.
Yes, this is Jimmy. Ever since I was a kid and I learned about the men walking on the moon, I wanted to be the first human to walk on Mars. And so I used as I grew, I took studies that direction, and I learned that we could grow oxygen and that we can grow water. But one of the largest stumbling blocks was the electromagnetic field of Mars was too weak to maintain an atmosphere. And my question is there a way that we can create a stronger electromagnetic field for the planet? Thank you. Bye.
Okay, well, Mars has been in the news ever since NASA said that, yes, we are going to Mars sometime after 2030. But the question is, why is Mars such a barren, bleak place? Well, it has very little atmosphere. Atmospheric pressure is 1% that of the Earth, and it's basically made out of carbon dioxide. But why? Why did Mars lose most of its atmosphere and, as a consequence, lose most of its liquid water? Because once upon a time, there were liquid oceans on the surface of Mars. And the answer you correctly pointed out is that Mars has almost no magnetic field. A magnetic field is very useful because it acts like a shield protecting you against the solar wind. The solar wind is very faint, but it buffets the atmosphere of every planet and blows a lot of the molecules into outer space. So because Mars has almost no magnetic field, it has no protection against the solar wind, which in turn blows the molecules of the atmosphere into outer space, causing Mars to lose 99% of its atmosphere. Now, let's say we terraform Mars. Let's say somehow we're able to raise the temperature of Mars and inject methane and other kinds of greenhouse gases and raise the temperature of Mars. The question is, won't we lose the atmosphere again? Isn't it basically a pointless exercise in futility to try to terraform Mars when the atmosphere is going to be blown off anyway? Well, yes and no. First of all, even if you create an unstable atmosphere of Mars, it's good for a few thousand years. So, in other words, yes, we can create, with tremendous expense, an atmosphere for the planet Mars. It would cost hundreds of billions to trillions of dollars, but it's going to be stable for thousands of years. Then, thousands of years later, you'll probably have to do it again because, of course, the atmosphere, the newly formed atmosphere, will gradually leak out. But there's also another factor involved. If you raise the temperature of Mars sufficiently, it means that the polar ice caps will begin to melt because they're made out of dry ice and ordinary ice. And as the polar ice caps thaw out, it releases more greenhouse gases into the atmosphere, which accelerates the heating of Mars. So we have another effect taking place, a runaway greenhouse effect. The warmer Mars gets, the more the polar ice caps melt, releasing more greenhouse gases into the atmosphere, which raise the temperature even more. So there is room for hope. Even though it may cost upwards of $1 trillion to initiate this process, once it starts, it generates enough heat to sustain it for thousands of years. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. Well, moving right along now, let's take the next listener phone call.
Hi, my name is Solomon. I'm calling from Wilkes-Barre, Pennsylvania. 103.1 FM is the station I'm tuned to. My question to Professor Michio Kaku is that in most explanation of gravity and most depiction of what gravity look like, they show us a fabric and whatever objects that are pushing down on it causing gravity. My question is, if there is no up or down in space, how does gravity indent space-time like a fabric? It just doesn't make sense to me. If you could please explain that.
Okay, well, you ask a question that a lot of people are asking, and that is, we have this picture that space-time can be viewed as a fabric like a trampoline net. So think of a trampoline net and then drop a bowling ball in the middle of the trampoline net, and the bowling ball, of course, sinks. Then you take a marble, you shoot a marble along the trampoline net, and lo and behold, my God, it orbits. It goes in a circle. The marble goes in a circle around the bowling ball. Why? Because the fabric of the trampoline net is bent. Now, this is an explanation of how gravity then warps the space-time around the Earth, and that's why the Earth goes around the sun. That's why you are sitting in your chair right now. Why are you sitting in your chair? Most people would say you're sitting in your chair because gravity is pulling you down. But Einstein says, nope. That's not why you're sitting in your chair. You're sitting in your chair because the Earth is warping the space-time around your head, and it is pushing your head into your chair. In other words, gravity is a push and not a pull. There is nothing pulling you down like gravity toward the center of the Earth. Space is pushing you down into the Earth. Now, what this questioner asks is, the analogy. Isn't the analogy wrong? Because the analogy itself requires gravity. Gravity pulls the bowling ball down into the trampoline net. So, aha, it's circular. I got him. I showed that Einstein's theory is wrong because it uses gravity to explain gravity. Well, just remember that it's only an analogy. Perhaps a better analogy would be as follows. It was Shakespeare who once said that all the world is a stage, and we are like actors and actresses making our entrances and exits on the stage of life. Well, now imagine that the stage, this empty arena called space-time, is warped. And as you walk across the stage, it is impossible to walk in a straight line because of the warping of the stage. Or take a sheet of paper. Crumple the sheet of paper and put an ant on the sheet of paper and ask the ant to move in a straight line. The ant cannot. It's buffeted to the left, buffeted to the right. Now put the sheet of paper in outer space. Now there's no gravity. There's no gravity. And then you ask the ant, can he move in a straight line? And the ant would still say, no. I try to walk in a straight line, but every time I try, I hit a fold, and I go to the left, I'll go to the right. So in other words, the thought experiment of Einstein is correct. The curvature of space gives you the illusion of a force. But the analogy of the bowling ball, the analogy of the trampoline net, uses gravity, and so it is slightly defective. A better analogy would be to put the sheet of paper into outer space and put an N on that sheet of paper, and then you are not referring to gravity at all to explain gravity. Welcome back to Science Fantastic with Professor Michio Kaku. Yes, this is your opportunity to share your thoughts on national radio. Okay, moving right along, let's take the next listener phone call.
Hi, Dr. Kaku. This is Alan from Denver, Colorado. And I had a question about life on Europa or any moon surrounding Jupiter. The question is, would Jupiter's magnetic field shield the moons from solar radiation? Because as we know, on Earth, we need our magnetic field or life couldn't exist. Would that same shield exist for the moons of Jupiter? Thank you.
Well, it turns out that our space probes, as they approach Jupiter, sometimes they're overwhelmed by this barrage of radiation. Jupiter is quite radioactive. And in fact, when you turn on your TV set and you see that snow when you're between channels, especially with the older TV sets, where does that snow come from? Believe it or not, much of it comes from Jupiter. That's right, Jupiter is a gigantic creator of electromagnetic disturbances, and it also has a magnetic field. Now, as you correctly pointed out, a magnetic field can protect you against the solar wind. Think of Mars. Why is Mars a frozen desert? Mars is a frozen desert because it's lost most of its atmosphere due to the solar wind. Because Mars has no magnetic field to speak of, it has no shield to protect itself against the harsh ionizing wind that comes from the sun and blows the remaining atmosphere of Mars into outer space. So the question is now, Jupiter has satellites going around it like Europa. We think that Europa has a liquid ocean underneath the ice core. How do we know? Because of tidal forces. Tidal forces are enough to generate heat, volcanic heat, at the center of Europa, hot enough to melt the ice cover of Europa, creating an ocean. In fact, we've estimated the size of that ocean, and it's actually in volume larger than the oceans of the Earth. And the Earth, of course, is much bigger than tiny Europa. And so then the questioner asks, the comment, the solar wind, is it deflected by the magnetic field surrounding Jupiter? Well, I think what the questioner is getting at is any life form on Europa protected from the solar radiation? And to some degree, yes. To some degree, Jupiter's magnetic field acts as a shield protecting Europa. However, Jupiter itself has a tremendous spray of radiation emanating from it, and so I don't think it's much of a consolation prize. In other words, any life form on Europa will have to live underneath the ice cover because the radiation from Jupiter is quite intense. So yes, Jupiter does deflect some of the solar radiation coming from the sun, dampening the radiation that would hit a moon of Jupiter. But that doesn't mean that life forms on Europa are let off the hook, because Jupiter itself generates a tremendous amount of radiation. Okay, well, let's move right along to the next listener phone call.
So my name is Tom. I'm calling from St. Petersburg, Florida, on 820 AM News. My question is regarding the phenomenal Philadelphia experiment. We've seen the documentaries. I've seen the documentaries, quite impressive. And we've seen the movies, part 1 and 2. The government officially denies the existence of time travel, but some scientific factors prove otherwise. Now, what exactly happened with the Philadelphia experiment back in 1942, 1943? So they tried to hide shit from the enemy, and they happened to get really well hidden and disappearing. Thank you.
Well, you ask a question that I often get on email, and that is, what about the Philadelphia experiment? As you correctly pointed out, it's a Hollywood movie, a movie in which scientists from World War II experiment with electromagnetic radiation on a battleship and accidentally sent the battleship backwards in time. Well, let's go back to the origin of the story. It goes back to the year 1955. In the year 1955, Albert Einstein died. And it was in all the papers that he could not finish his fabulous unified field theory, the theory of everything. A theory, by the way, which I work on professionally. Well, because of that, many people speculated what could possibly have been in that unfinished theory of 1955. Then an astronomer and also a writer on UFOs receives a letter in the mail stating that, yes, he was in the Navy, and yes, Einstein completed his unfinished work. It was a misnomer in the press. He actually completed the work, and the work talked about gateways and time machines and so on and so forth, and the person says that he witnessed things disappearing because of Einstein's unified field theory. Well, that person has never been tracked down. Most people think it was, in fact, a hoax. This entire story based on one letter referring to Einstein's unified field theory. First of all, I work on Einstein's unified field theory. That's what I do for a living. We even have a better version of it called string theory, which we think is the fabulous theory of everything. Does it allow for wormholes? Yes, it does allow for gateways into perhaps other universes, perhaps gateways into the past. But there's a catch. There's always a catch someplace. And that is, you can also calculate the energy necessary to create a gateway through space and time. And it is fabulous. It is the Planck energy. It's a quadrillion times the energy of our largest machine, the Large Hadron Collider based outside Geneva, Switzerland. In other words, the letter was a hoax. It was a clever hoax because it tried to piggyback over all the press coverage given to Einstein's unfinished unified field theory. So yes, we think we can finish that theory. Yes, it does allow for wormholes, but the energy necessary to open gateways through time is way beyond anything that could have been assembled in 1943, which is when the experiment supposedly took place, or even hundreds of years into the future. Well, I'm afraid we are out of time in Science Fantastic. Good day.